All right, everyone, this is chapter 9. We're going to take a look at different strategies to solve quadratic equations or equations with degree 2. We did start this in chapter 6 a little bit when we looked at solving by factoring, which is a great technique. We're going to look at other ways to solve and different kinds of things that can happen when we look at quadratics. So we're talking about graphs that are parabolas. So being able to look at things like this and talk about what their solutions are. That's the places where the graph crosses the x-axis. So thinking about where those locations are, what different options that we have to be able to solve. So let's take a look at this first method or first strategy, which is called the square root property, where we can solve an equation just by taking a square root or the inverse or opposite operation of squaring. So we're going to take a look at that strategy first in this section 9.1. So I'm going to go ahead and cover this up so we can focus our attention. When we talk about a squared equation, we're looking at undoing that squaring to solve for what value makes that true. So for this first equation, m squared equals 64, what we're asking ourselves really is what number times itself gives you 64, and what possibilities would there be for that? So the square root property just basically means that the square root is the inverse or the opposite operation of squaring, and we're going to do that on both sides. So we're going to do the opposite operation, making sure that that squared term is by itself first. So we always want to isolate or get that squared term by itself. So isolate the squared term. So if there's only a single variable term here, we get it by itself. So undo. So what times itself gives you 64? Well, 8 times 8 would give you 64. So one of the square roots is definitely going to be 8. But here's the thing we need to remember. A negative 8 times a negative 8 will also give you a 64. So it's technically going to be plus or minus 8. So we can write it together using that plus or minus, or you can say m equals 8 or m equals negative 8. Remember, that's that union where we're doing all of the solutions, everything together. So when we square root a variable term, we have to remember that there are two possible solutions, either positive times a positive or negative times a negative. All right, let's take a look and see how this letter B is a little bit different. If you notice, the squared term, the variable term that's squared, is not by itself. So we need to get it by itself first. There's only a single variable term, though, so we can just solve for it. Think of your x squared as your big variable that you're trying to get by itself. So I'm going to add that 54. So we have 3x squared equals 54. And then we're going to go ahead and divide by 3. Oopsies. And so 54 divided by 3, go ahead and figure that out. That would be 18, I believe. And then to undo squaring, we're going to square root. Now, here's where we need to have a conversation again. For sure, we know it's going to be plus or minus for the same reason as the last one. But 18 isn't a perfect square like 64 was. So what are our options for dealing with what we get for our answer? One option is to simplify that radical like we were doing earlier. So breaking this down into the biggest perfect square that divides into 18 times what's left over. So what's the first perfect square that divides into 18? Remember your perfect square list: 4, 9, 16, 25, etc., etc. Going up the line, the first one that's going to divide in there is 9. So 9 times 2, and the square root of 9 is 3. So we get plus or minus 3 square root of 2. So again, we can write it together with the plus or minus, or you could say positive 3 root 2, and then also negative 3 root 2. So you can write it either way. So if you want an exact answer, that's what we need to be dealing with. If you wanted just to get an approximate, you could grab your calculator and just type in what is the square root of 18 and see what that value is. So that's another option that we have for us if we don't want to worry about an exact answer. So it makes sense. It's a little bit bigger than 16, so a little bit bigger than 4. So we could say approximately about 4.2. So if we wanted an approximate answer, we have that option as well. We're going to try to stick to the exact answers, so we're going to be looking for more of this, but realizing that if we wanted a good guesstimate, we can use our calculator. So always isolate that square term first, and then you're going to square root both sides. So that's our process that we're looking at. So we're going to take that inverse or opposite operation to be able to find those values. All right, let's take a look at a few other settings that we can do very similar things, but they look a little bit more involved. For this one, it looks like we don't have a square term that's by itself, but actually it is, because this whole thing right here is the base. That's what's being squared. So we actually can solve this one the same exact way we did the last one. That base is by itself already. There's nothing added up, like say out here, that I'd have to move or anything like that. It's all by itself. It's the squared thing equals a number. So we can actually go right ahead and take the square root on each side. And when we do that, the square root of something squared, we get what the value is underneath. That's the whole purpose of this, is it undoes what's been done to that base. Now over here, we get plus or minus 6, right? We get either positive 6 or negative 6. Because remember, again, positive times a positive a negative times a negative are both going to give you that same result of 36. Okay, so what does that mean? Well, we have some solving to do now. This x isn't by itself. I have to think of that as two separate equations then. I have to think about when it's equal to positive 6 or when it's equal to negative 6. This is kind of like when we did absolute value equations. When you take the square root, we get absolute value happening. There's two places on the number line where we're going to be 6 units away from 0. So we solve each of these independently. So we're going to solve them both the same way, though. We're going to add 5. So either x equals 11 or negative 6 plus 5 would give us a negative 1. And if you put either of those back into the original, so 11 minus 5 squared should give you 36. And negative 1 minus 5 squared should also give us 36. And if you check your answers, 11 minus 5 is 6, so 6 squared for sure. Negative 1 minus 5 is negative 6 squared, also 36, absolutely. So we end up with two different answers. So we're always isolating the square term, taking the square root on each side, and then doing whatever we need to do to solve if we need to. So like in this case, we had an expression as a base. We had to do a little bit of work to solve for it. So we're going to try one more like that, a little bit more involved and maybe not so quite nice of a number, but really similar kind of statement. So we have this big yucky base, right? Squared equals a number. So again, the base that's being squared is by itself. So I'm going to go ahead and square root both sides right away, which is going to give me 3x plus 1 equals, and this is the really important part again, plus or minus square root of 2, right? It's either positive or negative. So we're undoing that squaring and we have that value. Now, how is this different than the last one? Well, 2 isn't a perfect square, right? So there's no way that I can actually do this and get an exact answer that has a nice whole number. It's not going to happen because square root of 2 isn't a perfect square, but we can still work with it. So I'm going to go ahead and set up those two equations like I did the last time, and I'm just going to write it with the square root of 2. I know that's not super enjoyable to look at, but we can work with this. All right, so now we're going to solve each of them. So we're going to subtract 1. When you do that in each case, so I'm going to kind of do these at the same time, you're going to have 3x equals. Now for the other side, you can decide how you want to write it. It doesn't really matter. You can put the radical first or the number. It doesn't make any difference, or the whole number. You can decide what's easier for you. But you can't actually put them together because it's not a whole number. So I'm just going to write what I would do, like say on my calculator if I was going to get a decimal equivalent. So I'm just going to write square root of 2 minus 1 and negative square root of 2 minus 1. And then our last step, we're going to divide both sides by 3 in each of them. So you're going to end up with x equals square root of 2 minus 1 over 3, or x equals negative square root of 2 minus 1 over 3. You could combine them, put them together if you wanted to. Otherwise, you can leave them separately. Some people write the negative 1 part first because that's a little bit easier for you. So you could put them together and say negative 1, and it would be plus or minus square root of 2 all over 3 then if that were easier, because we have the positive version and the negative version. So we have both solutions here for each of those. So it's a little bit worse when that number's not a perfect square, but we still do the same thing. We're just solving for the x. So undo what's been done to that variable term. All right, well, there's lots of different examples of real life situations where we would solve an equation like this. So one of them has to do with the distance and the time of a falling object. So it says the d is the distance in feet. An object falls in t seconds. So it doesn't have, it's regardless of weight and air resistance. So if we take a look at the time it falls, so say something falls for 5 seconds, we could figure out with this formula how far it would fall. So they did, Galileo was one that did a lot of work with this, dropping objects from the Leaning Tower of Pisa. If you've ever seen cool pictures of that, or the people that go and try to stand and get their picture taken, like it looks like they're holding up the Leaning Tower of Pisa, kind of fun. But you can actually, they did a bunch of experiments and figured out that this was always true. It didn't matter how heavy it was. Every falling object followed this this pattern having to do with the time that it falls and the distance that it falls. So let's do the Leaning Tower of Pisa so you can see what Galileo did in his experiment. So it was 180 feet tall. So that's our distance that it's falling, is 180 feet. We can figure out then how long would it take for the object dropped from the tower to fall to the ground. So how long would that take? So in this formula, we know what the distance is, and we want to solve for the time. Now, you could also, if you wanted to figure out going the other direction, you could say, well, what if something falls for this many seconds? How far would it fall? So this formula would work in both directions. All right, let's see if we can solve that. So is the square term by itself? It is not. So there's a 16 out front. So we need to move that 16. So I'm going to undo multiply by 16 first. All right. Lovely picture of Galileo there. 16 divides into 180 how many times? This may not be a nice number. I don't think it is. I think it's 11 and a quarter, but that's okay. We have a calculator. We can deal with that. In this situation, does it make sense to get an exact answer? Probably not. If you're going to tell someone, hey, how long did it fall? You're probably not going to say the square root of something, right? People look at you funny. You'd probably say it's about this many seconds. So I think it's totally fine to talk about a decimal answer here. So we're going to square root. So we're going to get t is approximately, I'm going to do my approximate, and we're going to take the square root here. So let's go ahead and do that on your calculator. So we're going to take the square root of 11.25, and we get 3.35. 3.35. And what units were we in? Well, that was in seconds, right? T seconds, so in seconds. So it'd take a little bit over 3 seconds for that to fall, that 180 feet. Now, remember how we always talked about, oh, it's plus or minus, plus or minus, plus or minus. Does it make sense in this situation to talk about a negative times a negative? Well, no, it's time, right? We're talking about how long something takes. So in this, our domain, what makes sense is only positive values. So when we think about time, we're only going to look at positive numbers here. So in real life applications, we have to think about domain. So it's a really cool formula to see the relationship between a falling object and how long it takes and the distance that it falls. So we're going to finish up with kind of a cool example of using this formula as well. If you've ever seen these on different shows or things like that, and they do like marksman things, and they throw something and then they do that. If you've ever done trap shooting or things like that, you can see very similar things happen, but the people that have really quick reaction time can do these really quickly, and this kind of blows me away here. So they have this expert marksman can hold a silver dollar, drop it, so you can see him have his hand up here. He's going to drop that and then shoot the coin before it passes his waist. So he basically is dropping it and is able to do that with his reaction. So if the coin is falling, we'll say about 4 feet. So from like his height level and then dropping down. So it's like holding it over his head, dropping it. How long between when he drops it and is the coin shot? So we're looking for the time it takes to fall that 4 feet. So we're looking for that time. So this is kind of crazy when you think about what this speed is. So let's go ahead and do this solving and see what we come up with. So the distance that it dropped was about 4. We have a squared term again that we're solving for. I want to get rid of whatever number's out front. So just like the last one, I'm going to go ahead and divide by 16. Now I want you to reduce that fraction for me. So 4/16 reduces down to, divide each of these by 4, right? Would be 1/4. The reason I had to do that is I think we can do this in our head then. If we square root then to undo squaring, it's approximately, actually this one's going to be exactly because of the values that it is. Remember how we treat square roots of fractions. We can do the numerator and the denominator separately. Great time to review that. So what times itself gives you 1? Well, 1. What's the square root of 4? 2. And this is in seconds. It takes half of a second for him to be able to do that. So it's dropped 4 feet already, and he was already able to get that. Just kind of blows me away how accurate that is and how quick. So that relationship is always true, and that's been back to Galileo's age of being able to deal with that. So the idea of using a square root to solve is a really helpful tool when we're solving quadratic equations that only have a squared term. So when we think about when would we use this, what is it appropriate for? We use this for when we're solving things that have only a square term and no linear term. We can use the square root to undo.